Start.
Thank you. Okay, thank you, Amina. Thank you for your introduction. And thanks to all the organizers for the kind invitation. I'm Xiunan Wang from University of Tennessee at Chattanooga. I'm very glad to meet you all here and to present my research in this artificial intelligence for pandemic seminar. And today I'm going to introduce a new method for forecasting the daily confirmed cases of COVID-19 by using differential equivalence and machine learning. And this is a joint work with Dr. Wang at the University of Alberta, Dr. Puya Ramsey at Brock University in Canada, and Dr. Xiunan at National Institute for Mathematical Sciences in Korea, and Dr. Mark Lewis. He's previously in University of Alberta, and currently he's in the University of Victoria in Canada. And my presentation will be based on these two papers. In the first paper, we introduced a new method that is a hypothesis-free bridge, which connects the disease dynamics to the non-pharmaceutical intervention policies. And in the second paper, we applied the method in the first paper to forecasting COVID-19 daily confirmed cases under imperfect vaccination in the United States. And so far, we have suffered from the COVID-19 pandemic for more than 3 years. And just a few days ago in my class, a student told me that she has been tested positive and cannot come to class. So the virus is still around us. And these two graphs show that by the end of last year, over 100 million people in the United States have been tested positive. And among them, more than 1 million have lost their lives. So in order to better control the pandemic and to prepare for future emerging and re-emerging infectious diseases, it's important to accurately forecast the daily confirmed cases so that policymakers can make correct decisions, choosing the most cost-effective control measures against the pandemic. And in order to accurately forecast the daily confirmed cases of the disease, we need to be clear about what factors about the daily confirmed cases. Actually, the daily confirmed cases of the disease are strongly determined or affected by the transmission rates. And the transmission rates are strongly affected by the non-pharmaceutical intervention policy data and the human mobility data. And here's a list of all the non-pharmaceutical intervention policy data, intervention policies. So some policies here, for example, testing, contact tracing, and facial coverings can directly affect the transmission rates, although they may not change the human mobility trends. Some other non-pharmaceutical intervention policies can change human mobility trends, and then the human mobility trends can affect the transmission rates. For example, the policy of school closing will cause more children to stay at home, and so their mobility at the school area is changed, and the transmission rates at the school are also reduced. So in this project, we'll use a machine learning model to connect the NPIs and the mobility data to the transmission rates. That is a hypothesis-free bridge connecting the NPIs and mobility data to the transmission rates. And once we are able to predict the transmission rates, we will be able to predict the daily confirmed cases. And speaking of predicting daily confirmed cases, so far there are mainly two types of models. One type is mechanistic models, The other type is the machine learning models. Mechanistic models such as OD, PD, SDE, or DDE models are highly intuitive, but they are less competent in making predictions, and usually hypotheses need to be made on the form of the transmission rate. For example, if we use the least square method to estimate the transmission rate, then we need to assume a specific form for the transmission rate. And in contrast, the machine learning models are more powerful in making predictions, but they are non-intuitive and perhaps less reliable if trained with fewer data instances, especially in the beginning of the outbreak of some pandemics. Due to the lack of enough data, in that case, machine learning models may not be quite useful. And in this project, what we want to do is to combine the advantages of these two types of models to create a new framework for forecasting the daily confirmed cases of COVID-19 under the influence of NPIs by a hybrid model of ODEs and GBM. So here ODE represents ordinary differential equivalence, and GBM represents the generalized boosting machine learning model or gradient boosting machine learning model. And this graph shows the big picture of this project. So we start from this ODE model, and we created an inverse method to estimate the transmission rates from epidemiological data. And then we put the estimated transmission rates into GBM to connect with the non-pharmaceutical intervention policy data or human mobility data for training. After training, given future NPIs, that we can predict future transmission rates based on their training experience. And eventually we can substitute the predicted transmission rates back into the ODE model to predict the daily confirmed cases. So this is the idea of this project. And here's the data about the non-pharmaceutical interventions. So some beginning with C represent the containment measures, and those beginning with H represent health measures. So these policy data are obtained from our World in Data website. So the curves represent the policy indices, and they vary between 0 and 4. So the larger the policy indices represent, the measures are taken at a stronger level. And the study period is from the beginning of April in 2020 to the beginning of April in 2021. And we also use the human mobility data obtained from Google website. So we care about these 6 types of human mobility data. There are the mobility trends in retail and recreation, grocery and pharmacy, parks, transit stations, workplaces, and residential. So for example, in this figure here, the yellow curve represents the mobility data in parks. And you see during the months around August, that's the summer season in the United States. And during the summer, people prefer staying outdoors more often than in winter times. So the mobility trends during these months are higher in parks, similarly to other places, and also give some interpretation. Okay, so next, so there are 2 parts of our hybrid model. The first part is the mechanistic ODE model, and the second part is the machine learning model. Now let's look at the first part. So we partition the total human population into these 8 compartments. S represents the compartment of susceptible individuals, and E represents the exposed ones, And we consider two groups of infected people. I represent symptomatic infected. So these are people who are infected and meanwhile they have symptoms. And A compartment represents the asymptomatic infected individuals. So if an individual infected but without symptoms, then after they finish after the incubation period ends, then they will enter the A compartment. And both people in A and I compartment can recover. So in that case, they will enter the R compartment. And some people with symptoms can even lose their lives. So they will enter the death compartment. And in this model, we consider two compartments for the vaccinated individuals. V1 represents those who are partially vaccinated, and V2 represents those who are fully vaccinated. And we also consider the breakthrough cases for the vaccinated individuals. That is infected, that is the vaccinated people can also get infected. So you see, so susceptible people after get the first dose of vaccination, they will enter V1 compartment. And after the individual receives the second dose vaccination, then he will enter compartment. And both V1 and V2 compartment individuals can get infected. So in that case, they will enter the exposed compartment. Okay, so here's the diagram of our model. And here's the model. Here's the ordinary differential equilibrium system. So in this system, we only write down 7 equilibriums. So because the dead compartment is decoupled, so we do not need to write down the equilibrium for the dead people. So in the first equilibrium here, beta of T is the time-dependent transmission rate, and the theta E, theta A are the relative transmissibility of the exposed and asymptomatic infected individuals compared to the symptomatic individuals. So theta E and theta A are parameters smaller than 1 and greater than or equal to 0. And capital N on the denominator represents the total population size. Eta of T is also a time-varying parameter. It's the first dose vaccination rate. So after the susceptible individual getting vaccinated, it will enter this V1 compartment here. And gamma of T is the second dose vaccination rate. And let's go back to the second equilibrium. Second equilibrium here, epsilon1, epsilon2 are the relative risk of infection for the vaccinated V1 and V2 compartments respectively. And the reciprocal of the parameter delta will represent the average duration of the exposed period. And once the infected individuals, after the incubation period ends, then the individual will enter either I compartment or A compartment. And we assume that a proportion P of the infected individuals will have no symptoms, and the rest proportion 1 minus P will have symptoms. Here, mu of T is also a time-dependent parameter. It's the disease-induced death rate. Ri and Ra are the recovery rates for these two compartments respectively. Okay, so this all the constant parameters, we can estimate them from published data. And for some time-varying parameters like the vaccination rates, eta of T and gamma of T, and the disease-induced death rate, mu of T, we can also estimate from the vaccination data or death data. But for the transmission rate, beta of T, is not easy to estimate because transmissibility cannot be observed directly. So there's no data to describe the transmissibility. And so once we are able to predict the transmission rate beta of t, then we can use this model to plot the solution curves, to plot the curve of daily confirmed cases. So the key point is to predict the transmission rate beta of t. And that is what we hope to get from the machine learning model. And in order to make the machine learning model to provide us with the future transmission rate, we need to provide the machine learning model with some known transmission rates so that they can be trained. And in order to get some known transmission rates, we created this inverse method. And the central idea of this inverse method is to discretize the ODE system. So here SEIAR V1, V2 represents the variables in the model on the case day, and D of K represents the number of cumulative deaths on the case day. And we use Y of K to represent the number of new infections on the case day. So the time series of Y of K will be the notification data of daily confirmed cases. And that is what we want to predict, right? We want to predict the daily confirmed cases. And in reality, actually, the reported data of daily confirmed cases come from the positive testing results. And in the United States, usually an individual will go to get a test only if the individual has symptoms. So it's reasonable to use the first term on the right-hand side of this equation for the symptomatic infected compartment to estimate the daily confirmed cases. So that is 1 minus P times delta times E of K is approximately equal to Y of K. Then from that, we can derive the time series of the exposed compartment. So that is E of K will equal Y of K divided by 1 minus P times delta. And we can also obtain the time series of V1 and V2, and as well as some other the other initial values from reporting data. After we get all these necessary time series data and the initial value data, we can run this iteration to get the time series of all the other compartments. And the key point is to derive the time series of the susceptible compartment. And once we get the susceptible compartment time series, we can add up the S equivalent, V1 and V2 equivalent to obtain this equivalent. And then we can inversely solve for the transmission rate beta from this equivalent. So again, here we need to discretize this equivalent, then we can get the time series of beta. So here on the left figure here, the blue curve represents the estimated transmission rates obtained from this inverse method. And if we substitute this estimated transmission rates into the ODE model, we'll see that the obtained curve of daily confirmed cases fits perfectly well with the reported data of daily confirmed cases. So this means the estimated transmission rates obtained by the inverse method can be used as training data. So it can be, should be reliable to be used as training data. Okay, so next we will proceed to the second part of our hybrid model, that is the generalized boosting machine learning model. So we partition the data into two parts. One is training part and the other is testing part. So since we obtain the transmission rates from the inverse method, then we can put them into the GBM model as the response variable. And meanwhile, we put the policy data and the human mobility data into GBM as the predictor variables. Then the GBM can be trained based on this variable data. And in future, when we provide the policy data and mobility data as predictor variables, then the GBM can return us the predicted transmission rate. And then we can substitute this predicted transmission rate back into the ODE model to plot the solution curves, to plot the curve of the daily confirmed cases. And this table shows the training and testing durations. So we trained the model for different lengths of days, varying from 231 days to 329 days. And our training durations started on April 4th, 2020, and they vary from for different lengths of days. And the testing duration starts right after each training duration. And all testing durations last for 35 days in order to make sure the prediction is accurate, is reliable. If we predict the model for too long time, then it's not reliable. And we use two criteria, MAE and MAP, to evaluate the performance of our prediction. And from this table, we can see that if we use only mobility data to forecast the daily confirmed cases, then the average MAP is the largest. And if we use policy data, all the policy data, then the MAP becomes smaller, so that is better. Well, if we use both mobility data and part of the policy data, then we can get the smallest MAP. So this is the best case. So this table indicates that it's necessary to incorporate policy data if we want to increase the accuracy of predictions. And the next, I will show two sets of selected numerical simulation results, prediction results. So this first set of results is when the data, when the model is trained for 245 days based on all the policy data. So on the left figure here, the blue curve is the transmission rates obtained by the inverse method. And the orange curve here, is the trained transmission rates. And the yellow curve is the tested or predicted transmission rates. So, and then we substitute the orange and the yellow transmission rates into the ODE system to plot the curve of daily confirmed cases. Then we obtain this right figure here. So in the right figure, the blue circles represents the reported data or notification data of daily confirmed cases. So that are your data. And the orange curve here are the curve of daily confirmed cases plotted by using the trained transmission rates. So that is by using the orange transmission rates in the left figure here. And the yellow curve of daily confirmed cases is plotted by using the tested transmission rates here. So we can see the training part fits quite well, almost fit 100%. And the yellow curve here doesn't fit perfectly well, but it also gives the general trend of increasing to a local maximum and then decreasing. So in this case, the MAP is about 5.2%. And we also get the ranking of the relative influence of all the policy data in this case. So we see that the most influential policy is restrictions on gatherings, and then followed by testing policies, school closing. And we also found that if we train the model for different lengths of days, then the ranking of this policy data also changes. But restrictions on gatherings is always the most influential policy. And this is the second set of results. So we trained the model for a longer period. This is trained for 315 days. And by using both policy data and part of both mobility data and part of the policy data. So again, in the left figure here, the blue curve are the transmission rates obtained by the inverse method. And the orange curve are the trained transmission rates. And the yellow curve is the predicted transmission rates. And after we use this trained transmission rates and predicted transmission rates to plot the curve of daily confirmed cases, we can see their fitting results in the right figure here. Again, the training part fits quite well, including those peaks and troughs, so it fits perfectly well everywhere. And the yellow curve also gives the general trend of decreasing for this part. And in this case, the MAP is smaller, is about 4.99%. And in this case, we also see the ranking of this mobility data and the 4 policy data. So in this case, the testing policy is far more important than all the other data, and then followed by facial coverings and contact tracing. Okay, so here's a brief summary of our project. First, we built a hybrid model consisting of a mechanistic ordinary differential equivalence model and a gradient boosting machine learning model. And we developed an inverse method, and that method is called discrete inverse method that obtains the transmission rate inversely from the other variables in the ODE model and then feed it into the GBM to connect with the policy data or mobility data. And we found that the inclusion of data on non-pharmaceutical intervention policies can significantly improve the accuracy of the predictions. And the most influential predictive variables in training the GBM are the policies of restrictions on gatherings, testing, and school closing. Okay, that's all from my presentation. And thank you for your time and attention.
Thanks, Xiunan. Are there any questions from the audience?
Hi. Thank you. That was a very excellent presentation. You're very good at explaining things to someone who's not a computer scientist. I understood most of that. I was just wondering, when you said when you trained the data for longer, that the influential factors changed. Why is that the case?
So your question is, when we train the model longer?
I think it was back one.
This one?
Yeah, so you said you trained it for 45 days, but then if we trained it longer, then this graph changed?
Yes, so we found that if we train the model for different lengths of days, then the ranking of the relative influence of the variables also changed.
Do you know why that is?
I don't know. So I think it depends on the policy data. Yeah. So from the policy data, we see they vary dramatically. So during different period of time.
So it's due to the variations in the training data.
Yeah. So probably when we train the model for different lengths of days, then different variables. Different policy data play different weight of roles. So
yeah, okay, that makes sense. And I just have one more question. Like, it's really good that you can say these are the, like, from a public health perspective, like these were the things that were most influential for transmission. But given that you can have a pretty good model to predict the number of cases per day. Could you flip it the other way? Because I think what would be really useful, like public health people would be interested in, instead of just saying these are the influential factors, could you, I guess, use some kind of data to input into the model to predict different scenarios? So like if the vaccination rate was this is how many we'd predict if everyone was wearing face masks. Like, could you do it that way and actually predict based on different situations so that you could have sort of different predictions at the end of this is how many cases we could predict if this is the kind of prevention we had in place? I think that would be quite convincing to a public health audience.
Yes, I think that's a very good question. Yeah, I think we can predict daily confirmed cases under different scenarios. Yeah, so we can assume, so in the model here, so we can assume different vaccination rates, or based on different future vaccination data time series. And under different scenarios, we can predict the daily confirmed cases.
Yeah, I think that would be really, really useful for public health people.
Yeah. Thank you.
Any more questions?